So if we look at a finer slice and we get a velocity for that slice, and we look at smaller and smaller slices, till we eventually get down to a slice that has no distance. It only has a velocity. So that is becomes my instantaneous velocity. So the way we write that, we have our instantaneous velocity v, which is a function of t. And again, all this means is that as t varies, so does velocity. It's equal to delta x over delta t. Now all delta means, the Greek letter delta, all that means is a difference on x. For instance, up here, delta x is x of d minus x of h. Here, delta x is the distance between my driveway and NASA Road 1. Here is the distance between Tallywood Crossroad and Plantation Crossroad. And we're going to want this to go smaller and smaller and smaller and smaller, so we get a better and better picture of our actual instantaneous velocity. So the way we're going to do that is something called a limit, which we write as LIM. The limit, as t approaches 0, of delta x divided by delta t equals something we call a derivative, dx dt. So v sub t equals dx dt. V is our instantaneous velocity, and the instantaneous velocity is how fast you're going at any particular point in time, and of course that corresponds to a particular point in space. And if you remember from us talking about points, point has no width or length, so it's that very instantaneous velocity at that infinitesimally small point corresponding to an equally infinitesimally small point in time. And that's all that is. Dx dt is a derivative. If you haven't been exposed to this before, don't worry about it. It's just a definition. So velocity, instantaneous velocity, equals to dx dt. Delta time divided delta distance divided by delta time as the delta gets very, very small. Actually, as it goes to 0. Like we were saying, velocity is variable. It changes with time. You know, when I'm out here on the highway and I'm going, 80 miles an hour, and there's, some idiot in the road, and I have to slow down to 40 miles an hour, my velocity changes from 80 to 40. And, that's what we call a deceleration. I've decelerated from 40 miles an hour from 80 miles an hour to 40. Then I go around the idiot, and now I accelerate back from 40 to 80. So our velocity is changing with time, just as our position changes with time based on our velocity. And so in a similar kind of argument, we can say that acceleration, also a function of time, is equal to dv dt, delta in velocity divided by delta in time. And we can take it one step further. You're driving along at 80 miles an hour, and there's some idiot in front of you, and you slow down to 40. And then the idiot in front of you, he's driving a pickup truck with a bunch of stuff in the back, and a ladder falls out. And so the ladder falls out, and you're trying to slow down to miss the guy anyway. Then the ladder, all of a sudden there's a ladder on the road in front of you, and you quickly decelerate all the way to 0 to miss the ladder. Well, that change in deceleration, where at first you were just slowing down and now you're coming to a dead stop, you know, when you're decelerating, there's a force on your body pulling you towards the front of the car, and your body's resisting that force, and then you really hit the brakes, and your body jerks forward as that change in deceleration or change in acceleration, and we call that event, which causes your body to jerk forward. Obviously, we call it the jerk, and the jerk is the derivative of acceleration with respect to time. So we have position x. If we change our position in a certain amount of time, that's velocity, dx dt. If we change our velocity with time, that's acceleration. It's equal to change in velocity per time. If we change our acceleration in time, that's equal to change in acceleration divided by change in time, dA dt. And these can go on and on and on forever. For our purposes, position, velocity, and acceleration is about all we need to worry about. We'll leave the jerk to Houston traffic. Okay, so we've looked at how to determine velocity based on change in distance and time, but what if you're trying to figure out how far you've gone given a particular velocity and a particular time? Obviously, you know, we know the basics, right? If I know that my average velocity is 45 miles an hour, and I know that I did that for 6 long hours, then obviously x equals b times t, and that gives me my 270 miles, the distance between Dallas and Houston. And that's great if, you know, if I'm traveling at a constant velocity, but of course I'm not. So I'm going to look at velocity again. I'm going to look at a slightly simpler graph than the one we used to get from Dallas to Houston. I'm going to say that velocity is moving something like this. Maybe I'm going up and down mountains, I don't know. And I have a couple points here, T1, and another point here, T2. So in the time between T1 and T2, traveling at the velocity indicated here, how far do I go? How do you figure that out? Well, what we do is, for a first order approximation, and in engineering we like to do everything as simply as possible, so a lot of times we'll just do an approximation, and you know, if it's good enough, it's good enough. Sometimes we have to do a little bit more, but let's say that every so often, and this is 1, 2, 3, 4, 5, 6, 7, 8. Let's just say this was an 8-hour trip, and every hour we measure what our velocity is. So we're going to divide our graph of velocity into slices. And then we're going to estimate the velocity during that slice with whatever the velocity was when we started the slice. So for this first slice, it's there. Second slice, velocity is there. Third one, fourth one, fifth one, sixth one, seventh one, eighth one. So I've got these distances, x1, x2, x3, and so forth, that I can now calculate based on this. We'll call this a pseudo-average velocity. It's not the average over the entire trip, and it's not the instantaneous velocity, but it's a velocity over some fixed delta time, an hour or a minute or whatever. So now I can say that my total distance x, well, obviously it's the sum of all these individual distances. It's how far I went in my first increment of time plus how far I went in my next increment of time plus how far I went in my next increment of time, and so on and so forth. And then each of these increments of time is simply equal to average velocity during that time times delta t, where delta t is the distance between any two of these points. So x1 would be the distance that I went as I traveled for this velocity, v1, for delta t number of minutes or hours. So then my total distance is just the sum of these, x1, x2 plus x3. So v1 delta t plus v2 delta t plus v3 delta t plus however many more slices we took. In this case it's 8, but again that's entirely arbitrary. Well, okay, let's just say up to 8. So the way we write that in mathematical language, instead of writing out the sum longhand, we use an operator called sigma. The Greek letter sigma stands for sum, and we would write this as the sum of v sub I delta t as I goes from 1 to 8. So we're going to do something similar to what we did when we were looking at instantaneous velocity, and that is we're going to make our delta t's get very, very small. As t gets smaller, delta t gets smaller, we have more and more slices, until eventually as t approaches 0, we have an infinite number of slices. And our average velocity during a slice approaches our instantaneous velocity. So we're going to rewrite this as x equals the limit as t approaches 0 of the summation of over I of v sub I delta t, and that's equal to something we call an integral, which is denoted by a big S. So the limit of the sum over I of v sub I delta t is equal to v sub t, our instantaneous velocity, times dt, our instantaneous time, and then x, which is of course a function of time because your position changes with time. We'll call it x of t. So x of t equals integral of v sub t dt. And we can get to that another way. If you recall that v sub t equals dx dt, then if we multiply both sides by dt and move the x over here, I'm going to say dx equals v sub t d sub t, or v sub t dt. We took the integral of both sides, and an integral is just the opposite of a differential. The integral of this equals the integral of this. The integral of the differential of x is just x of t equals the integral of v sub t dt. So you can get to this point either way.